Right, in the previous lecture we covered everything about matchings. From this lecture we will talk about connectivity, and the first topic is to review the things that we did in the discrete math course to connected graphs. But let's begin with the definition of k-connected graphs. So G is k-connected. Okay, let me start with the connected. Just review the definition. Connected if for every pair x, y of vertices, G has a path from x to y. Right? Now graph is k-connected if it satisfies two conditions. So the first condition is graph is not too small, has more than k vertices, and second condition is whenever for every set x of less than k vertices, G delete x is connected. So that's what we mean by k-connected. So such a set is called a vertex cut. So a set X is a vertex cut of size L. Okay, we don't have to say size. If X is subset of vertices, such and G delete X is disconnected. Right, so we will use this quite often. And we have seen the definition of cup vertex. A vertex V is a cup vertex. I mean, we could say that a vertex is a cup vertex if G delete V is disconnected, but to cover more general cases, we say that G delete V has more component than G. All right. Now, let's see what are the k-connected graphs. Okay, so what happens if k is 0? Graph is 0 connected. What does that mean? If you apply the definitions, it has to have more than 0 vertices, so the set of vertices is not empty. And for every subset of size less than 0 vertices, G delete X is connected. This is trivially true. So that's what it means to be 0 connected. What about 1 connected? Well, now it has to have more than 1 vertices and any set of size less than 1. So it's so you don't delete anything. So G is connected. How about 2 connected? Number of vertices is greater than 2, and now if we delete empty set, then it says graph is connected. And if you delete one vertex, right, then it says that G has no curved vertex. All right, this is all trivia from the definitions. Now there is another way of deleting something, right? So that's edge connectedness. So G is K edge connected. Yeah, so for this we talk about graphs with at least 2 vertices. Okay, is K edge connected if so when do we say graph is K edge connected? If I delete less than K edges, graph is disconnected. Okay, so for every set x of less than k edges, G delete x is connected. So it's a similar definitions. Right. For vertex connectivity, we delete vertices. So why this connectivity is useful? Because for instance, we want to build a telephone network, and the idea is no matter how, like let's say 10 vertices are removed, we still have a connected graph. Then in that case, we want to have 11 connected graphs. For edge connectivity, we would say that no matter how less than k edges are destroyed, we still want to have a connected graph. So that's why we want to have a k edge connectedness. But can you simplify that, right? So how do we make a disconnected graph? If G is not k edge connected, then G has a partition, right? AB such that all edges from A to B have been deleted, right? Because G delete X is disconnected. What does that mean? That means number of edges from A to B is less than K, right? The number of edges between A and B is small. I mean, it's less than K. Now there's no need to delete any other edges. So let's call this is an edge cut. So on edge cut, so we rewrite this delta A so that okay. For a subset of vertices of G, we write delta A to be the set of edges having set of all edges having one end in A, another end in VG minus A. Okay, now such a thing is called an edge cut. Yeah. Any set of edges that can be written as delta A for some A, which is non-empty and not equal to P of G, is called an edge cut. Edge cut of G. So now this observation says that graph is k edge connected if and only if it has no edge cut of size less than k. No edge cut size less than k, right? Because one direction, if graph is k edge connected, trivially you don't have edge cut of size k less than k, because when you have an edge cut of size less than k, you can delete those edges. How about converse? If graph is not k edge connected, then we must have a partition like this. We must have a partition like this, and that partition gives me k edge cut. Okay, here I should say A, B are non-empty. All right, so that's k edge connected graphs. So let's see the examples. So 0 edge connected. So let's assume that number of vertices is in these two. So what is 0 edge connected? Then if we don't so you don't delete any edges, graph stays connected, so that means G is connected. What about one edge connected? Now graph is connected, and if you delete any edge, graph stays connected. And such an edge is called a cut edge. So an edge is a cut edge if G delete E has more, okay, let's say more components than G. Okay, so something like this is a cut edge, right? When you delete it, you increase the number of components. Okay, why do I say, instead of saying graph, okay, I mean, I want to use this, I want to call this edge to be a cut edge later, so that's why I'm using these definitions. All right, now what's the relations between K connected graphs and K edge connected graphs? Here's a, right, so okay, let's compare these two. So for instance, what should we start? I mean, it's easy to see that, okay, not every, okay, so two edge connectedness does not imply two connectedness. Why? What's the example? For instance, well, I might have an example like this, parallel edges. That's one example, but that's a trivial example. How about this? If I add if I say that number of vertices is bigger than 2, still, is it, do we have a counterexample? Well, actually there are many. Okay, I might say this, right? Anything else? Right. I mean, this has many parallel edges, but if you ignore that, I mean, if you want to insist the simple, but still you have a counterexample like this, right? Any edge, you delete any edge, graph is connected, but when you delete the vertex in the middle, graph is disconnected. So two edge connectedness with some extra condition doesn't necessarily imply two connectedness. However, one case, I mean, there will be homo problem where this is actually true, but let me not mention this. But the converse is true. So here's a theorem. Let G be a graph with at least two vertices if G is K connected, then G is K edge connected. Why is this the case? Now, if you look at this statement, it seems quite trivial, but actually there are certain points where it could go wrong. Right. Yeah, so let's see what happens. So if K is less than 1, then it's trivial. Let's not do it. Less than or equal to 1. So if K is 0, then it's trivial, right? Number of vertices. It's only about number of vertices. Every graph is 0 edge connected. Oh, no. think I'm cheating a little bit, right? Every graph is so graph is zero connected, but that doesn't mean that graph is zero edge connected. Oh, right. No. Actually, something's wrong here. I was cheating a lot. Okay. Where did I cheat? Okay. So graph is zero edge connected. If you delete less than zero edges, graph is connected. But there's no way to delete less than zero edges, so this is always true. Or right? So this is true statement. And one edge connected, if you delete less than one edges, you have connected graph. So G is connected. How about two edge connected graphs? Then G is connected, and if you delete one edges and the graph is connected, it has no cut edge. All right, now makes more sense. Okay, so zero is connected. So zero connected implies zero is connected. One connected implies one is connected. Sure. So we can assume the case n is 2. Now, suppose G is K connected. Right? And G has an edge cut that A of size less than K. Right? So you have A and B, and number of edges between them is less than K. Now, there are a number of cases to consider actually. If I look at the set of vertices meeting all these edges, and this set of vertices meeting all the edges on along the cut, if this set is smaller than K, I mean that's smaller than K definitely, then I can try to delete that and graph should stay connected. What does that mean? That means this part is empty, right? Because this has size less than K, if I need to delete it, graph should stay connected, but there's no other edges from A to B, so that means this whole part is empty. And conversely, this thing is less than K, so that means this whole part is empty, right? So that's the situation. But then, okay, let me first write it down. Yes. Okay. Let's use matrix. So we may assume. So let B be the VG minus A. We may assume that A is bigger than us. A has more vertices than B. All right. And so this is X. Let X be the set of vertices of A incident having neighbors in B, then size of X is less than the number of edges, which is less than K. So G delete X is connected, means that A is equal to X, right? There are no other vertices. Sure. Now, if graph has more than if graph G has more than 2k vertices, we could have been, this could be the end of the proof, because this set has size less than k, this set has size less than k, the graph has less than 2k vertices, but that's not the end, right? We only know the graph has more than k vertices, so there's a still gap. Now, what we do is the following. So here's a vertex in X, which is now equal to A and B. Now, what happens if there is a vertex V having only one neighbor? If A has a vertex V having a unique neighbor W in B, then in that case, G delete A minus V union W is disconnected, right? Because the V has no other neighbors on B side except W. Okay, so neighbors of V are either here, neighbors of V are either here or there. So if we have this thing, but size of A minus V union W is equal to size of A, this is still less than K, contradiction. Therefore, every vertex in A has at least two neighbors in B. Right? Every vertex in A has at least two neighbors in B. So the number of edges, so delta of A is going to be at least twice A, because every vertex in A has at least two neighbors. But remember, we assume that size of A is bigger than size of B, right? So that is at least the number of vertices. But remember, number of vertices is bigger than K. So that's contradiction, because we started by assuming that delta A is less than K. So that's the proof. So the ending of this proof is a bit tricky, but still. All right. So far I didn't talk about the two connected graphs. Now let's talk about two connected graphs. There's a nice equivalence relation arising from two connectedness. So we say two edges E and F for for two edges E and F of G, we say E is equivalent to F if E is equal to F, or because I want to satisfy reflexivity, I want to make this relation to be reflexive, or there is a cycle containing both E and F in G. I will say that this has a theorem. Then set of edges with this relation is an equivalence relation. So remember, what is the equivalence relations? You satisfy three properties, right? E is equivalent to E, and E is equivalent to F, then F is equivalent to E. This is called the symmetric. This is called the reflexive. And the last property is If E is equivalent to F, F is equivalent to G, then E is equivalent to G. This is transitive. So we need to prove three of these three properties, and this is trivial. This is trivial. The first one is trivial by definition, and second one is trivial. So what's left is to prove the last one. If there's a cycle containing E and F, and there's a cycle containing F and G, we want to prove that there's a cycle containing E and G. All right. So suppose, okay, so yeah, so here, so let C be a cycle containing E and F, and D be a cycle containing F and G. So here you have a E and F, and we may, our goal is to find the cycle containing E and G. Oh, by the way, we assume that E, F, G are distinct. Because if any two are equal, then there's nothing to show. And we may also assume that C and D are distinct. Okay, I mean, we can assume that G is not in D and E is not in, okay, G is not in C, E is not in D. All right. Now, our goal is to find the cycle containing E and G. Now, what could happen? For instance, in the easiest case, we may have something like this. Then we have a cycle like this. That could be easiest. But we may end up like this, and then have to choose, right? So that's the idea. I mean, in general, the picture looks very ugly, right? This could be cycle, and still we can do something like that. So by following D, we have two paths, P1, P2 from the ends of E, G, such that no internal vertex that exactly one vertex of each pi is on the cycle C. So what I want is I want to find the two paths from each end. So 1, 2, by following D, right? So remember, D is like this and C is like that. Oh, so that's a bit cheating. So D could be like, so this is G, this is E, this is F. Right? So what's happening? Well, I got this for my P1 and this for my P2. Right? So what I wrote here is we follow this cycle D until we hit the first vertex to meet C. Now, then by taking a subpath of C together with P1 and P2, we have a cycle containing both E and G. I mean, I didn't write all the detail, but what we can see here is, well, in this case, I can combine them. And this is indeed a cycle because P1 and P2 has no other, right? Since P1, P2 have no more than, I mean, exactly one vertex on C, this forms a cycle, right? I was worried about wrong proof where you take this and blue may intersect, right? This is incorrect, but this will never happen. So that's the end of the proof. So that's the equivalence relation, and that allows us to characterize two connected graphs very nicely. So let's all right, so let's do it. So theorem. Okay, this theorem. So we start with the connected graph. And let's say you have more than two vertices. Okay, let's not say that. See what happens. So we want to say that the following are equivalent. So the first one is G has no curved vertex. The second one is okay. For any pair VW of distinct vertices. Okay, no, okay, any pair EF of distinct non-loop edges, G has a cycle containing both E and F. And so this is for any pair of edges you have a cycle. So in other words, everything is equivalent under the previous relation except the loops. The last condition is for any pair VW of vertices, G has a cycle containing both V and W, or number of vertices is 2 and most 2. Okay, so that's the claim. So what are the graphs without curved vertices but connected? Okay, so 1 implies, let's see why 1 implies 2, right? And that's where we use transitivity of these relations. So suppose if E and F share an end V, so E is here, F is here, share vertex V, right? Then, so this is the first case, and G delete V what happens? If I delete V, then this delete V is connected. So that means G delete V has a path from one end of E other than V to another from an end of F other than V, right? So I can find the path in G delete V connecting these two vertices. So that means G has a cycle containing E and F. And both E and F are not loops. So there's a non-loop, so this vertex is not equal to V. This vertex is not equal to V. So therefore, E is equivalent to F. Whenever they meet, right? But what happens E and F are not meeting? In general, there is a path P from E to F because G is connected, right? So that means you have a E, E1, E2, you have sequence EK minus 1 and you have EK. So E is equivalent to E1, E1 is equivalent to E2, up to EK minus 1 is equivalent to EF, and then you have F. So by transitivity, E is equivalent to F. Okay, so that's the proof. How about 2 implies 3? If you have two vertices VW, now we pick a pick an edge E incident with V and pick an edge F. Okay, I want to choose a non-loop edge. Pick a non-loop edge incident with W, and since number of vertices is bigger than, okay, let's assume, we may assume number of vertices is bigger than 2, because otherwise we are done. Then we may assume that E and F are distinct because graph is connected, right? So you have a V and W, graph is connected, there must be at least one edge connecting V and W to outside the world. So you gotta choose this one for E or F. Then other edge will not be equal to that, right? So that means by 2 there is a cycle containing E and F. Okay, how about 3 implies 1? If you have more at most 2 vertices, then graph looks like, graph is connected. So previously you have 2, yeah, so it's trivial, yes, trivial if number of vertices is at most 2, right? You don't have any cut vertex. Now if if suppose that for any pair of vertices there is a cycle containing both of them, then if G delivery is disconnected, then there is no cycle containing X and Y. Let's say X is on the left one component, Y is in another component. So when X, Y are in distinct components of G delivery. So that's contradiction. So that's it. So having no cup vertex is same as having such a thing. So it's almost, right? So no cup vertex is same as saying almost like you have a cycle for any pair. Right? For any pair of vertices, you have a cycle. Later, we'll talk about the generalization. But anyway, here's a theorem due to Whitney that so assume that G is two connected if and only if for all distinct vertices V W of G, G has a cycle containing V and W. Well, another way of saying same thing is for all distinct vertices V W of G, G has two internally disjoint paths from V to W. So two paths, we say two paths P1, P2 are internally disjoint if no internal vertex of one is a vertex of another. Okay, so I want to say I cannot say that they are vertex disjoint because they looks like this. So these two vertices are in common, but I want to say that no internal vertex is a vertex of another, right? So that's what we mean by internally disjoint. So that's another characterization of two connected graphs. So if you want to say to somebody the graph is two connected, you just need to show two internally disjoint paths between every pair of vertices. If you want to say the graph is not two connected, you may need just find one cup vertex or one either you say the graph is disconnected, or you say, oh, okay, here's a cup vertex, then you delete it, graph is disconnected. All right, so let me show you two theorems about the constructions of two connected graphs. So first one is called the ear decompositions. So adding an ear to a graph G is to add a path. Okay, so first pick a vertex, pick two distinct vertices, VW of G and add a path from V to W whose internal node, okay, vertices are not on G. So what does that mean? So for instance, let's say this is my graph, and adding, so this is an ear. So such a path is called an ear, right? So pick these two vertices. In this case, I added a path of length 1. I might add a path of length 2, or I might add a path of length 3. Okay, and then I might add a path of length 2 like this. So starting from any two connected graph, and if I pick two vertices and add an ear, then I end up with another two connected graphs. Why? Because between any pair of vertices here, I used to have a disjoint a cycle containing them. Between any okay, I mean, is that a better way? Okay, let's use the cup vertex definition. So graph is connected anyway. If I delete any vertex here, graph is connected. Any vertex here, graph is connected because that's connected. If I delete anything on the path, on the ear, graph is connected, right? So it's easy to see that if G is two connected, then G plus one ear is two connected. Now here's the theorem. G is two connected if and only if you can actually build it by adding ears repeatedly. G can be built from a cycle of length at least 3 by adding loops and ears. Adding loops is always allowed because that doesn't change any vertex connectivity. So that's the theorem. And prove one direction is trivial because graph, oh no, the other direction. That direction is trivial because we already observed that whenever you start with two connected graphs, when adding an ear is two connected, adding a loop is two connected. So what about the non-trivial directions? Let's start with the largest subgraph which can be built by such a thing. So let H be a largest, okay, instead of largest, let's say maximal subgraph of G that can be built from some cycle of length at least 3 by adding loops and ears repeatedly. Now, how do I know that such a subgraph exists? Well, the thing is, I have to show that every two connected graph has a cycle of length at least 3. Well, one way to see that is first delete all the loops, delete all the parallel edges, right? So first make a simple graph. And if you change graph to a simple graph by deleting loops and parallel edges, you still maintain connectedness, two connectedness, right? Why? Because deleting one edge out of parallel edges doesn't change connectedness, because we only delete vertices and see whether the graph is connected or not. So I can find a simple graph which is underlying graph from G, And then this graph must have cycle, because if I choose any two distinct vertices, there is a cycle. But since you don't have parallel edges and loops, this cycle has length at least 3. So I must have at least one cycle of length at least 3, and that's the beginning, right? So that's a graph which can be built in such a way. So H must exist. Then among all possible H's, I choose the maximum one. And since there are only finitely many subgraphs, you must be able to find a maximal subgraph with that property. And then, so I didn't write the reason why such a thing exists. Then H is an induced subgraph. Because otherwise we can add an ear of length 1, right? So here is an H. If I have a missing edge, if I had an edge like this, then I can add it. So H is increased, so that's contradiction to the maximality. So H is an induced subgraph. So if V of H is not equal to V of G, then you have a vertex outside. Right. So what can you do? Then pick an edge E inside H and an edge F incident. Okay, I have to choose a non-loop edge. Non-loop edge E and a non-loop edge F incident with V. So I have a F and I have E. Now G has a cycle containing both E, F. Right? So that will then, by this cycle C has a subpath that is an ear to H, right? Because I follow this path in two directions. There will be vertex that hits H for the first time. Then this red part is an ear. Then this is contradiction to the maximality. Contradiction to the maximality of H. Okay. Because I can add the H plus this ear. That's gonna be H prime, which is bigger. Right. So every two connected graph can be built from cycle of length at 3 by adding ears. And this will be useful when we try to prove something on two connected graphs by induction, because when you have some property, I want to prove it for two connected graphs, and what you do is you first find you claim by induction, and you say that this is true for all graphs with a smaller number of edges. Now, by ear decompositions, you can build your graph by adding ears repeatedly. So there will be a last ear. So your graph G is always H plus some ear, or G is a cycle, or G has a loop. Right? So you can always say whenever graph is two connected, then you can find another two connected graph which you can add, and then to that you add on 1 year to make your graph G, or graph is a cycle, or you have a loop. In three cases, you can always probably apply induction hypothesis to this smaller graph H and deduce what you want. So it's very useful for induction. Okay. Now I want to show you the next theorem, which will be also useful for the induction. So let G be a two connected graph, then G has an edge E such that G delete E or G contract E is two connected, unless there's one count example, I mean not one, but anyway, unless graph is too small. So this is another useful theorem for the inductions, because whenever you have a graph, two connected graphs, I can reduce it to a smaller two connected graphs and then apply induction hypothesis to two connected graphs and recover the theorem. So why is this true? All right, I'm back. So to prove this theorem, let's assume that G, right, so G contract E is not connected, not two connected. And we can assume that E is not a loop, because if E is a loop, then G delete E is a two connected, right? All right, and so that means, let's say xy be the ends of E. So what used to be like this, right? I mean, I know that this is G contract E. You have more than one components, right? And when you go back, it looks like this. So this is graph G, where you have a partition of the graphs into two parts where there's no edge from left to right. I'm not saying that this is connected, that's connected, right? I mean, you might have more than two components like this, but I can always find the partition so that there's no edge from left to right. Okay, now since G is two connected, for any pair of vertices, there is two internally disjoint paths. For any distinct pair VW of vertices, G has two internally disjoint paths. From V to W. Right, now why do I care? Because if I have a two vertices here, I mean, all right, And the thing is, so we want to prove the graph is two connected. So I need to find the two internal decision paths from V to W. Is this best way, by the way? If I have a V here and W here, then the only way you can have a two paths is to use both X and Y. That means you cannot use E, right? So if V, W are in distinct components of G delete X delete Y, then both X, Y have to be used. Okay, let me say in notations, you have P1, P2, then X, Y in VP1, union VP2, and you cannot contain X and Y. Okay, I mean, let me say this way. We may assume X is in VP1 and Y is in VP2, right? So therefore, XY, the E, cannot be used in P1 or P2. So G delete E has two internally disjoint paths. From X to Y, right? So if VW are in distinct components, I know for sure that there are two internal disjoint paths. What happens if they are in the same components? Okay, so X and Y. Right, and if I have a same component, it is possible, right? Okay, so we may assume, yeah. Thus, we may assume VW are in the same component. Say C1 of G delete X delete Y, and P1 uses E, right? So this is P1 and P2. Now, what should we do? In this case, we're going to use another component. Let C2 be a component of G delete X delete Y other than C1, okay? And I claim that both X and Y have neighbors in C2 because G is two connected, right? Because if X doesn't have neighbors to C2, then Y will be a vertex. Now once we have our neighbors here, neighbors there, and C2 is component, so it's connected, so there's a path. So then I can find the path from X to Y using vertices from C2. So G has a path from X to Y using internal vertices only from C2. let's say P. Then we can reroute P1 by P, right? So not using E, right? What we end up is, instead of P1, we go this, right? So I know that there is a path like this. So what we can do is, this is, instead of P1, we have now a longer path, and that's P2. So let's say this is P1 prime, then P1 prime and P2 are two internally disjoint paths. From V to W. So that means G is two connected. Oh, I think I'm cheating a little bit. What did I cheat? Okay, let me say this. So here, thus we may assume that there is a component C1 of G delete X delete Y such that both V, W are in VC1 union XY. It is possible that X or Y could be V or W, right? So this vertex V may be here or here. So I want to allow that. Okay. So that means for any, so far for any, we proved that for any pair of vertices, there are two internally disjoint paths, so graph is two connected. Okay, so that's the proof. So why is this interesting or useful? Well, when we want to prove some theorem, let's say you have a homework problem intended for two connected graphs, and you use this as a basic tool for induction, right? You say that your statement is true for all smaller graphs, and then now you need to make a smaller graph which is two connected. So you start with the statement and then you contract or delete an edge. One of them is two connected, and then you apply induction hypothesis, you get something. And now you only have to do, when you have to do now is to prove that the statement is true for your original graph by using the induction hypothesis. Okay, so that's it. Right, so that's it for two connected graphs. Okay, bye bye.